Good morning. I am Jim Haldeman with the Lesman Instrument Company. Thank you for taking the time to attend our webinar this morning. Our topic, control valve or metering pump, which do I choose? This webinar will be recorded and posted on our website for anyone to listen to at a later date. Please enter your questions in the questions section of the menu bar, and we will answer those questions at the end of the presentation. If we don't get the answers to the questions, we will follow up with you after the presentation has ended. We are pleased to welcome our speakers from Richard Industries. They are Matt Miller, who is the Chief Engineer for the LowFlow product line. Matt joined Richard Industries in 2016, where he worked on the new product development team and provided technical support for the LowFlow product line. Matt studied mechanical engineering at the University of Cincinnati. We're also joined by Harry Woebkenberg, who is the Vice President of Product Marketing at Richards Industries, where he leads product management efforts and acts as the Jordan valve and the LowFlow valve product manager. Harry has been with Richards since 2008. Harry, please proceed with your presentation.
Thanks, Jim, and thanks to everybody that's taken the time out of their schedule to join us this morning. A special thanks to Lesman for giving us this platform as well. We're going to talk today about control valves and metering pumps. And which one is most appropriate for your particular application. That's a choice that you're going to have. But hopefully this morning, Matt and I can arm you with some information that will allow you to make a better informed decision. So if I can get my screen to advance, there we go. Chemical dosing or metering defined. One of the textbook definitions is chemical dosing involves delivering a chemical substance into a fluid, usually as part of an overall process. So dosing can be as simple as having a chlorine float in your swimming pool and putting a chlorine tab in there and just, letting it disperse in the water. Or it can be as sophisticated as a dosing system that goes into the tens of thousands of dollars. For the purposes of our conversation here today, we're going to be talking primarily about chemical dosing in industrial environments, and it is a precise function. Accuracy and reliability are key. Whatever the system is, it has to be repeatable. Chemicals are expensive, so the choices that you make relative to your particular process are critical. You have to make sure you choose the appropriate components that deliver the quality and performance required to minimize cost and maximize performance. By most definitions, whether it be a metering pump or whether it be a centrifugal pump using control valves, they generally will be small flow volumes that are precisely dispensed at preset intervals. Varying flows require either manual adjustment or some form of PLC control. And metering pumps have valves, and if you use control valves, there's going to be a pump involved. So, both are viable, but again, there are several considerations that you're going to want to take a look at before you choose what kind of system you're going to use. Metering pumps. There's a ton of choices in that space. Some are a couple $100. Some can be $8, $10, $12,000, and that's going to vary based on your needs and the choices you make when configuring the pump that you're going to use. But they're used to add small and very accurate volumes of liquid to other fluid streams or vessels. They're also called dosing pumps or proportioning pumps, and it must be able to deliver liquid with an accuracy of greater than 3%. So, you know, you basically what you're talking about is an accuracy of, you know, within 3% of the desired set point. And that has to be across a wide range of discharge pressures. You will see that, you know, metering pumps, a lot of them are accurate to plus or minus 1%. So highly accurate. Where are they used? They're used across a variety of industries. Pharmaceuticals, a heavy population in water and wastewater treatment, food and beverage, power, the process industries, including chemical process and petrochem, and oil and gas extraction. So the liquids, the medium can be anything from fragrances and pigments in the production of toiletries or food or acids, and alkaline solutions for chemical processes and water treatment. And while metering pumps work effectively for many applications in different liquids, in most cases it's not recommended that they're used for moving various types of gases. What's a control valve? A control valve normally is defined as the final control element in a control loop. So generally they're used in a closed loop system. The control valve manipulates a flowing fluid to keep the regulated process variable as close as possible, again, to the desired set point. So a configuration like you see on the screen can be plus or minus 0.5% to the desired set point. Now, while a pump is manipulating or regulating flow, that's what a control valve does as well. The variables, it can impact our pressure, flow, temperature, level, or pH. And it does all of those by regulating or controlling flow. Where are control valves used? Well, control valves are used, again, across a variety of applications in a variety of industries. All the process industries, chem, petrochem, oil and gas, food and beverage, health and beauty, water, wastewater, power, textiles, hydrogen, which is an emerging market that where control valves are seeing a lot of play right now, and obviously pharma and biopharm. So these are used both in process and in utility applications. So process would be obviously process dependent. You know, utilities, you know, you'd be talking not so much about dosing applications, but other kind of control for steam, plant air, industrial gases, hot water, chilled water, lube oil. So, you know, those would be the industry or the utility applications. And, you know, again, process, especially in dosing applications, would pretty much be chemical in nature by and large. Okay, dosing applications. Common types of metering applications include maintaining a constant flow rate, regardless of differential pressure or media viscosity, delivering a variable flow to maintain a system parameter, pH control, for instance, injecting a discrete dose, typically required in batch processing. So, those are very typical of metering applications, and they're generally used in applications where one or more of the following conditions exist. So low flow rates, high system pressures, high accuracy is demanded. Dosing is controlled by a computer, microprocessor, DCS, PLC, or flow proportioning. Corrosive, hazardous, or high temp fluids, and viscous fluids or slurries needing to be pumped. So you can see there's a wide range of various applications that are considered dosing or metering in nature. Examples, specific examples of dosing applications would include, but not be limited to, chemical injection at water and wastewater treatment plants. And again, both dosing pumps and control valves have huge populations in water treatment plants and wastewater treatment plants. We've got a huge population of control valves out in Southern California, and most of the valves in that process are stainless would be at the low end, but we also go into high alloys based on the medium that's being injected into the water supply. They're all operated by stepper motor operators, so there's high resolution, great repeatability, and very precise dosing. Some of the medium that we use that those valves are used to control is sodium hypochlorite, caustic, sulfuric acid, fluorosalicylic acid. The materials that we use, stainless steel, alloy 20, Hastelloy C, and we also use PVDF valves for some of the very corrosive applications. So, and in the same plants, they also, and those are driven by centrifugal pumps, and the control is actually done by the control valves. But in the same facilities, they have a significant population of metering pumps, and they're used similarly for similar functions and for dosing applications. But again, there's a place for all of these, but it comes down to the specific application where you want to make a choice that's best for your specific application. Dye flow control on textile machines, corrosion inhibition skids in the petrochem industry, acid control in smelters and refineries, and chemical treatment skids in power plants. So those are all examples of dosing applications. To move on, again, there's control valves, generally speaking, have a little more versatility than just a metering pump. So this is just a list of other applications where control valves are used, which aren't specifically dosing applications. So these are more control, and again, we're going to control flow in order to control pressure, flow, pH, temperature. So again, just an example of some of the things that control valves will do in addition to dosing. And here's a few others as well. So lots and lots of applications out there, and I don't want to get too far off topic. So we'll get back specifically to the dosing here. How does a metering pump work? A metering pump moves a precise amount of liquid during a specific time period, yielding an accurate volumetric flow. And one of the, they transfer media in two stages, basically. There's an intake stroke and an output stroke. And during the intake, liquid is pulled into the pump cavity past the inlet check valve. During the output stroke, the inlet valve closes, the outlet valve opens, and the fluid is forced out. The flow may be varied by changing the stroke length or by adjusting the cycle frequency. And again, generally speaking, that can be done manually or through a PLC. They're used primarily to pump chemicals, can be solutions or others. In some cases, they can do slurries. In some cases, they can even do solids now. Technology has improved to the point where they can meter solids. There are a range of different metering pump technologies, and we'll take a look at those, but we're going to focus on just a couple that we see more often than not on the industrial side. But the critical application criteria include viscosity, temperature, pressures, flow rates, and materials construction. Obviously, they need to be compatible with whatever the medium is that's running through the particular valve. Most have a pump head and a motor with some adjustment mechanism, whether it be manual or electronic, and that depends on the manufacturer and the level of sophistication of the particular pump that you're working with. Okay, so how does a control valve work? There are three elements in a control loop, and like we said, the control valve is the final control element, and it varies the flow to change the controlled variable to the required set point. So the sensing element measures the process variable being controlled. Okay, we've got a set point. For instance, if you're controlling flow, so many liters per minute, so many gallons per minute or gallons per hour. And then the controlling element calculates, hey, you want it to be flowing more than this, so it's going to calculate the difference in the signal from the sensing element and calculate that versus the desired set point, and it's going to send a signal back to the final control element. It's going to tell it what to do, and it's either going to open or close, depending upon whatever the calculated error is. So here's a schematic of a very simple control system. Okay, you've got your input, and it's going to go through the valve in line. Okay, it will go. It'll experience load changes and disturbances in the process. We're going to measure. Okay, and again, we'll use a temperature sensor, we'll use a pressure sensor, we'll use, a Coriolis flow meter, whatever we might use, and that is going to send a signal back to the controller. The controller is going to calculate the difference in whatever the process condition is and the desired set point, and it's going to go back and it's going to tell the control valve what to do. So at a very high level, that's how a control valve works. Different, obviously, than the metering pump, but when you have the flow coming in, there's going to be a pump downstream. So, or upstream, I mean, my bad. And so, obviously you need some kind of motive force to move the medium through the line. Okay, this is a chart that I found that gives you, again, at a high level, kind of a comparison of various pump types And here at the bottom, we've included, what can you do with a control valve? Okay, so again, some of the fields don't translate from one to the next, but it's a handy little reference piece, and it goes into a bellows pump, diaphragm pump, peristaltic, and we're going to look primarily at diaphragm and peristaltic pumps today. Piston, syringe, these are all out there, but we don't necessarily see those as much in the industrial environments, but they are there, and they are all available. And then we have a low flow control valve, what it can do. There are actually versions that will go up to 12,000 psi, so they can handle high pressure. They're very accurate. Again, if you have one with a positioner, with a smart positioner, you'll be able to achieve accuracy plus or minus 0.5% to your set point. Okay, pump types. As I said, we're going to focus primarily on diaphragm pumps and peristaltic pumps, because in our experience, we see those more than piston, syringe, or bellows pumps. But these both have advantages, and there are a couple of weaknesses involved. A good friend of mine who used to, for many years, he's now retired, worked at a specialty chemical plant locally here. They used diaphragm pumps for chemical metering, and it was at one point it was a Morton plant, and then it became a Roman Haas plant, and ultimately became a Dow facility, and they did nothing but specialty chemicals, and they used diaphragm pumps. They liked them because there were only a couple of moving parts. They had the expertise in-house to be able to repair, rebuild, and test. So that's going to be one of the considerations. Based on some of the pumps, the complexity of the pump can make for challenging repairs and expensive repairs. Some of them not so much. Again, just like you can find a wide range of upfront pricing on pumps, the same thing with repairs. Some of the components might be machined to extremely tight tolerances, and the more sophisticated, obviously, the more challenging and more expensive it can become. And peristaltic pumps, there are some advantages to those as well. Sometimes referred to as hose pumps, but we'll get into those in a little bit more detail in the next few slides. So at this point, I'm going to turn it over to Matt and let him run with this for a while. So here we go.
Just taking a quick look at some of the different control valve types. Terry touched on it a little bit in some of the other earlier slides. Here at Richards, we typically focus on rotary or linear type control valves, rotary being your quarter turn, your ball valves, your butterfly valves, plug valves, and the linear being more typically used in the controlling aspect, specifically with globe style or needle style plug valves. And those come in a wide range of different styles. So the one you're seeing on the screen now would be an example of a pneumatic style, where it has an air-operated pneumatic actuator on top, which is what takes the signal from a positioner or other controlling device, and that's what actually manipulates the valve open or closed to obtain your desired set point for whatever you're trying to control. If you don't have air available, control valves can be motor operated. So as long as you have electricity, you'd be able to control those with a motor. We offer 3-way control valves, where if you want to mix two specific fluids into a common line, or if you have two lines and you want to divert them at different times, you can do that with a three-way valve. We offer bellows valves, which are more used on the more corrosive applications where you don't want any of the processed fluid getting out into the environment, whether it's bad for the environment, whether it's hazardous to operators or, plant facilities. Bellows are a good sealing type valve to prevent any leakage. We also offer temperature valves. So we have cryogenic valves on the low end, getting into the minus 300 degree operating range, where you would find liquid nitrogen or liquid oxygen or stuff like that. And then we also offer high temperature options if you're getting into the 700, 800, 1,000 degree territory. We have control valves to operate in that space. Quick note on some diaphragm dosing pumps. They can appear more cost-effective than peristaltic pumps, but they do have their challenges. One of the challenges that Harry touched on earlier was that the diaphragm pumps have sort of an intermittent cycle. So you have a suction stage and then a discharge stage. So it does not offer a smooth, continuous flow. It sort of gets a intermittent step-style flow, which I say disadvantage if that's the application it's going into. It's well suited to that. But if you're looking for something with a nice, smooth, controlled flow, a diaphragm pump might not be the most effective option. Diaphragm pumps have check valves on either side of the pump. So there's a check valve in the suction stage and a check valve on the discharge stage. If those check valves become clogged up or damaged in some capacity, the pump's not going to be able to control accurately, if at all. They can also create some shear stress on the fluid, particularly if it's a high velocity action. If your diaphragm is moving very quickly, pulling fluid quickly into the chamber and then pushing it out in a quick manner, some of that fluid could undergo stress that it's not intended to, which can cause problems on your heads and some of the check valves. And then another consideration is if routine maintenance needs to be performed. There's a couple more parts than you might find on a control valve that you need to repair and or replace at certain inspection intervals. Peristaltic dosing pumps. So these are the other form of dosing pumps that we're looking to highlight here. These pumps are very good at pumping particulate matter into lower pressure systems, because there's nothing to really clog. There's no additional check valves that are going to get clogged up or damaged, and this tends to be a more gentle pumping motion, so it's not going to damage delicate fluids within the tube. Sort of the opposite of the diaphragm pumps, where it could create those high shear forces. This is going to be a smoother sort of rolling action that is less damaging to whatever is going inside of the tubing there. These have more of an ability to pump gas-forming chemicals. Diaphragm pumps typically are used more on liquids, but if you're pumping something that could be a gas, a peristaltic pump might be a better option. Another advantage is that it does not, the fluid is always contained within the tubing that you see in the pump here, so you don't have interaction of the mechanical components directly interfering with the process fluid. Everything's self-contained within that tubing, so chances of wear and tear getting into the fluid are a little bit less. But one disadvantage is they don't typically do that well against high pressure applications. So if you need something in the several thousand PSI range to be pumped or controlled, the peristaltic pump might not be the best option. Here's a quick highlight on the LowFlow control valves. So for those not familiar, LowFlow is one of our brands here at Richards. Typically, it's our main control valve, and specifically for, as the name states, low flow. So you'll see on the second point, second to last point there, our control valves control from a CV range of 0.401 all the way up to a 10.0 CV. So that's a wide range of CVs for a ton of different applications. And for the most part, the valve itself is going to be the same construction. So it's not going to require tremendous footprint installation space, whether you're controlling from that super tiny CV all the way up to a larger 10.0 CV. It's basically going to be the same valve with different inner workings. We offer sizes ranging from 1/4 inch up to 2 inch on our LowFlow line. We have pretty much every end connection you can think of, whether it's threaded, socket weld. We have welded flanges. We have, different flange styles. I've seen 50 to 60 different flange specifications probably in my time here. So there really isn't a connection application that we can't do. We also offer a wide variety of construction materials. So Harry mentioned before, you get into, stainless steel is sort of our base default valve. But if you're interested in corrosive compatibility for your media, we offer Hastelloy C, we offer Monel, we offer Alloy 20. We even offer plastic valves if the chemical is going to be corrosive to metal but not plastic. So we have those options available. Some of the features of our LowFlow control valves include a rolling diaphragm. So that would be the diaphragm that is contained within the actuator. As the valve is given more and more of an air signal, that diaphragm will sort of roll over on itself and create a nice, smooth, consistent surface area upon which to act on. So that's going to result in a much smoother stroking action, which is in turn going to give you much better control of your flow or whatever process variable you're trying to control. We offer spring-loaded packing, what we call live-loaded packing. That's going to create a nice seal in your bonnet packing area to prevent any process media from getting out into the environment. We offer bolted body bonnet connections for quick maintenance or trim change. You just undo the body bonnet bolts and you can take the entire top works of the valve off without really having to change any of the finer connection points. On some of our other valves, we offer a threaded bonnet, similar to the bolted bonnet, quick disassembly there. And then we also have side-mounted positioners is our standard positioner option. So when you need very fine control, very good turn-down ratios, we offer positioners in the side mount or top-mounted variants if you need that good control. So as mentioned, both metering pumps and control valves sort of operate in the same space for a lot of applications. So some of the specifics when you're considering which one to use are going to look the same. But if you're looking at selecting a metering pump, you need to know stuff like the flow rate and discharge pressure. You need to be concerned about chemical compatibility, power source. How is the motor going to be supplied with power? The environment it's going into, the application that it's going to be controlling. the level of quality and accuracy, and then also things like the viscosity of the fluid. Is it going to be, nice clean water? It's not going to have any solids. Is it going to be a slurry mix? Or, in the case of recent pump developments, typical, full solids, might have the ability to be controlled at a reasonable level. And so those are some of the same selection criteria you're going to want to be aware of if you're looking at a control valve. You're going to look at your flow characteristic. Do you need a linear style plug or an equal percentage style plug, which I'll get into in just a slide or two. You need to be considerate of your upstream and downstream pressures and your pressure differential, the temperature of the fluid, things like line size, inlet and outlet typically would be the same, but we do offer variable line sizes if you want a 2-inch inlet down to a 1-inch outlet, for instance. We offer that. You need to take into consideration your allowable noise in your piping system, materials of construction, the valve action, whether it's going to be air opening the valve, which would be a reverse acting, or if you want air signal to close the valve, which is going to be what we call a direct acting valve. Metering pump characteristics. The actual flow rate is determined by the formula below. So your flow rate is going to equal your displacement times your number of cycles per unit of time. So that each pump is going to have a certain displacement. In the example of a diaphragm pump, it's going to have a displacement when it, on the intake stroke, and it pulls that fluid into the chamber and then pushes that out. And that can be determined by however many cycles you have in a given time frame to get your overall flow rate. And the image shown here would be a typical diaphragm pump kind of cycle. So you have one complete cycle consisting of the suction phase, which is going to pull the fluid into the chamber, and then the discharge phase, which is going to push the fluid out. And that would be considered one complete cycle. And as you can see here, it's not the smoothest of flow control. It sort of gives you that on-off, stepped motion, which, depending on the application, could be what you're looking for. If you're looking for consistent batch timing, but if you want a smooth flow, the diaphragm pump might not be the best option. So going back to control valve characteristics, at Richards we offer a couple different trim types. The quick opening is a trim type where you're going to get most of your flow right off of the opening stroke. So if you need a valve that's going to give you a large inrush of flow, basically as soon as the valve opens, quick opening is what you would want to choose. A linear is going to be just that. It's going to be a more idealized travel, so you get directly proportional flow versus travel. So the more you open up the valve, basically the more flow is going to result through there. And then what we call equal percentage is going to be sort of the opposite of the quick opening. It's going to produce equal changes in existing flow. So if you need something that's going to give you low flow over a wider opening percentage, equal percentage would be the trim option you would pick. Quick note on turndown. So turndown is basically the accuracy of maximum flow to minimum flow. Most metering pumps have a turndown of 10 to 1. So basically, how accurate is that going to be between 10% of capacity and 100% of capacity? I think that's a good number to have on hand. Some of the newer, probably higher cost pumps can get up to about 100 to 1, meaning you can operate in the 1% to 100% capacity. LowFlow control valves exist kind of somewhere in between there, depending on the CV. In general, the larger the CV for a control valve, the better turn down it's going to have, simply because you can get larger flow rates through that valve because of the larger CV. So something in our CV of 4.0 offering might get you a 50-to-1 turn down, but if you're on the extreme micro CV end of a 0.05 CV, for example, that turn down might only be 5-to-1 or 6-to-1. So you need to kind of have that in the back of your mind when you're selecting your control valve, what the application is going to be and the applicable turn down ratio. Next few slides, I'm going to get into some of the metering pump advantages. We like to say control valve is going to be better for everything, and since that's what the industry that we are in, but metering pumps obviously exist for a reason, so they do have their advantages. One of them being, diaphragm pumps are hermetically sealed, so if you're looking at hazardous fluids, they're a great option because, the fluid doesn't really come into contact with anything other than the body and the diaphragm itself. All of the fine, the fine parts, the gears and all that stuff are contained outside of the process fluid, so you don't have to worry about contamination or corrosion. Peristaltic pumps, capable of dealing with highly viscous fluids and slurries. So that's something that they can deal with better than low-flow control valves. If you have solid particulates, peristaltic pumps would be a good option there. And as mentioned before, they are highly reliable when they're properly sized and applied for the application. But control valves also have advantages themselves. They have the ability to adapt to fluctuating pressures because they're in that control loop that was discussed, with your sensing element and your controlling element. They can adapt on the fly to changes in the system. They're useful on gases, whereas the pumps are typically more used on liquid applications. They can be, fail open or fail closed, depending on when there's an upset condition. If the valve needs to close quickly, it can do that. If it needs to open quickly, it can do that as well. They provide positive shutoff when no flow is required. The customers would typically use that if they need tight shutoff, then they don't have upstream or downstream isolation valves, or even if the skid or the system they're going into does not allow for the footprint to install additional valves, the control valves can be used to provide positive shutoff. A wide range of CVs are available, and one of the main benefits of control valves is if you're in the higher pressure space, control valves can get up, low flow valves can get up to about 12,000 PSI of control. You're not really going to find a pump that's going to operate that high of pressure, but our control valves are able to withstand those high pressures. So, how do you choose? When are you going to choose a control valve, or when are you going to choose a metering pump? You need to take into consideration the accuracy and reliability, the long service life, which provides the greatest value. So you're going to have to perform a total cost of ownership to determine, is a metering pump or a control valve going to be the best option? And will you receive the required level of responsiveness and support? One of the things Richards is very good at is quick delivery times and local presence, as far as offering support and troubleshooting for our products. We provide training, and we provide required resources that are needed for accurate control and long life.
Well, thanks, Matt. And that's the end of the presentation. So again, we want to thank everybody who participated and was part of this morning. Jim, I know we're right up against it time-wise. We ran a little bit longer than we thought. We can, if people have time, we can probably do a couple questions right now, or if it's more convenient, we can go ahead and follow up on a case-by-case basis to answer any questions that any of the audience had.
Thanks, Harry. Yeah, why don't we plan on doing that? So if anyone has any questions or additional questions, please post them in the chat questions, or you can email them to me at jimh@lesman.com. So with that being said, I want to thank both Harry and Matt for their participation. I certainly learned a few things this morning, so I thank you for that. And with that being said, we're going to end the presentation. Again, thanks everyone for your time. Have a wonderful day.
Thank you.
Thank you.